Okay, I am going to solve homework 2 examples here. Yesterday's video didn't appear on Blackboard, so here I'm redoing it. The very first thing we did was notice that there was a typo here and that this is supposed to be megahertz rather than megaz's. And what I did here then was I want to find the period. The period is what we call capital T, and we know that the period and the frequency are inverses of each other. Therefore, the period is 1 over the frequency. But in order to plug into this equation, I'm going to first convert the frequency into hertz. So 20 megahertz, and if we're being very careful, we can say 1e to the 6th megahertz. No. Let's get it right, John. 1 megahertz, I want megahertz in the denominator to cancel, is 1e to the 6th hertz. And so this comes out to be 20e to the 6th hertz. Okay? You can kind of do that without multiplying by your conversion factor, but multiplying by the conversion factor is the technically correct long way of doing it. So now I'm going to go 1 over f and plug in 20e to the 6th for f. And because I've got hertz there, I know that t is going to come out in seconds. 1/20th is 0.05, and e to the 6th in the denominator is e to the minus 6 in the numerator. So this is 0.05 times 10 to the minus 6 seconds. If I write it with 3 decimals after the three numbers after the decimal point, e to the minus 6, I can identify this sort of as 50 e to the minus 9 seconds. Okay? And I guess it does ask for units of seconds, so technically I'm done with the problem, but I'm going to go ahead and write 50 nanoseconds also, because 10 to the minus 9th is a nano. Okay? Oh, look. Parts B and D are just asking me to move it to different units. Okay. T is equal to 0.05 e to the minus 6 seconds. To turn it into milliseconds, let's see, I get 1,000 times more milliseconds than a second, so I know it's going to be 0.05 e to the minus 3. But I can go ahead and write 1 second is 1,000 or 1e3 milliseconds and convert it that way, sort of the long way, maybe less prone to error, 0.05 e to the 3 milliseconds, or 50 milliseconds. 0.05 e to the 3 is 0.05 times 1,000, and if we move the decimal place over 1, 2, 3 places, we get a 50. Okay, 50 milliseconds. If we want to convert to microseconds, let's see, we already have e to the minus 6 seconds here, so the e to the minus 6 is a micro. T is equal to 0.05 e to the minus 6 seconds, but e to the minus 6 seconds is a micro, so that's 0.05 microseconds. Okay, hoping this helps. How long does it take for 1,000,000 periods to pass by? Well, the total time is 1,000,000, 1e to the 6th, times the time needed for 1 period. But that's what we call the period, t. That is the time for 1 period. So it's 1e to the 6th times t. And I already know t is, so this is 1e to the 6th times, and I'll just use this version of t, 0.05 e to the minus 6. The plus 6 and the minus 6 cancel, and I get 0.05 seconds, or 50 milliseconds needed for 1,000,000 periods to go by. Okay? Hope this helps. So this is what we call t by definition. By definition. Okay, there's the first one. Hope that's clear. second one, okay, so the first one was a traveling wave. It was an electrical signal in a wire at 20 megahertz. This would be typical of something like, what's in your USB wire, something like that, I think. But here now we have an infrared light signal. This is like your remote control or fiber optic communications signal. And these have incredibly high frequencies of something like 200 terahertz. And in fact, the frequencies are so high that we normally speak about wavelengths when we talk about infrared light. And so I will have you convert that to a wavelength below. But for now, we're going to calculate the period, t, and we're given the frequency, f, and that's just like the last problem. T is 1 over f. And I'm going to go ahead and write f as 200 terahertz, but also write that as 200 e to the 12th hertz. So it's really 2 times 10 to the 14th hertz. Wow. Okay, so this is 1 over 2e14, which is 0.5 e to the minus 14. So the bigger the frequency, the smaller the period. So now we have an incredibly small amount of time here. 0.05 times 10 to the minus 14th seconds. So if I can find my monitor here. And let's see, a nanosecond is 10 to the minus 9th seconds, right? So this is 0.5 e to the minus 14 plus 9, right? Well, let me not write it like that. Let's just convert this e to the minus 14 into nanoseconds and say 1 e to the 9th seconds is 1 nanosecond. So this is seconds here. So the seconds are canceling. And 14, negative 14, whoa, I've got this upside down here. I got 1 e to the 9th seconds is 1 nanosecond. That's completely upside down. It's 1 second, John, in the denominator. We want seconds to cancel. You just have to continuously correct yourself on these things. This is seconds. And I'm going to write 1 second is 1 e to the 9th nanoseconds. There we go. Nanoseconds are tiny. It takes 1 billion of them to make 1 second. So negative 14 plus 9 is negative 5. 0.5 e to the minus 5 nanoseconds. And I think that's how I left the answer. Oh, I just did part B there. So here's part A, seconds. And here's part B, nanoseconds. Okay, and I'm going to try to get in the habit of putting a big square around the answers because I'd like you to do that. It makes it much nicer to grade. Okay? Okay, so now I'm going to go ahead and now I've asked you for wavelength. And I know from my experience in the industry that, and I covered this just a little bit when I went over this. Let me remind you of the electromagnetic spectrum. We have visible light, which ranges in wavelength, lambda. Wavelength is lambda, from about 400 to about 700 nanometers. Okay? And that's going from the red to the blue in the rainbow. Okay? Infrared, lambda ranges from about, I don't know, I guess from about the 700, let's say 800, to, I don't know, I think maybe a few thousand, 3,000 or 5,000 nanometers. I'd have to look up where they officially say it ends. In any case, we expect that this is infrared light, and so we expect our wavelength to be somewhere in the range of something like 1,000 nanometers. Okay? And the equation that relates wavelength and propagation speed, v, and frequency, f, is this. V is lambda f. And since f is 1 over t, we could write lambda over t, and that shows how nicely the units work out. A propagation speed is in meters per second, lambda is in meters, and t is in seconds. Okay? And frequency is in hertz, so meters times hertz is the same thing as meters per second. In any case, this is the equation we're going to use, and we're going to solve that equation now for lambda. And I'm going to write lambda, I'm going to use the first version of it, is v over f. And I'm going to take the 2 times 10 to the 8th meters per second. There's no metric units on there, so I'm going to leave it as 2e8, and I'm going to plug in the frequency in hertz rather than terahertz. 2e to the 14th hertz. And when I do that, I'm going to get meters on lambda. Okay? The 2's cancel, and 8 minus 14 is minus 6. 1e to the minus 6 meters. Okay? And this is 1 micrometer, which is, in fact, 1,000 nanometers, just as we thought. Okay, good. If you're having trouble just doing these steps right here, please review the size of micro is 10 to the minus 6, nano is 10 to the minus 9th, and 1,000 times 10 to the minus 9th is 10 to the minus 6, which is a micro, 10 to the minus 6. Okay, and if I turn that into nanometers, hey, I just did it up here. 1,000 nanometers is this answer. Calculate the wavelength in units of meters, it says. So here's the answer for that part. And in micrometers, I already did that part too. There's 3 answers. Okay? So this is a typical wavelength of infrared light, lambda. And notice that I plugged in meters per second and hertz here and got out meters there. Okay? I'll keep on keeping on here. Let's see, problem 3. Here we're given a 5.7 gigahertz frequency, and this is more like a Wi-Fi frequency. Okay, this is like a 5 gigahertz Wi-Fi. Example. Okay, and so we are given F is 5.7 gigahertz, and I'm just going to immediately go to 5.7 e to the 9th hertz. Okay, convert it to standard units. And we're also given lambda is 5.25 centimeters, and I'm going to write that as 0.0525 meters. So once I have F and lambda in hertz and meters, I'm after the propagation speed V, and I just did an example with that. V is lambda F, meters in the numerator, seconds in the denominator, right, meters per second. And so I'm just going to plug in these 2 lambda and F values, and my V is going to come out in meters per second. 5.7 e to the 9th times 0.0525. And 57 times 525, I'm not going to try to do in my head. And I'll tap that out on my calculator. 5.7 times 0.0525 equals. And I get 2.99 e to the minus 1. So 0.299. And you may have noticed I didn't type in the times 10 to the 9th in my calculator, so I have to add that by hand. 0.299 E9 is 299 E6 meters per second. Yeah, or approximately 3 times 10 to the 8th, right? I divide by 100 here, and I'm rounding it off to 300, dividing by 100 here, and I multiply by 100 there. Right, 3 times 10 to the 8th meters per second, and this is c, the speed of light. Okay. Obviously, I cooked up this problem that way. How far does this wave travel in 10 microseconds? Well, this is our standard velocity is distance times time. You know, driving down the road equation. So how far does it go? D is equal to the velocity divided by the time. No. This is all wrong. I got this equation totally wrong. I am at risk of just writing down the complete wrong thing if I don't keep checking myself. I think I said it right. Distance is velocity times time. I have to talk myself through it here. Here's what I'm going to do. I'm going to say that the distance d is directly proportional to the velocity. That is, if I go twice as fast, I'm going to go twice as far in the given amount of time. And for a given velocity, if I go twice as long, I'm also going to go twice as far. So I'm okay with this equation now. Distance should be proportional to both velocity and time. And if I plug in my velocity here, 3e to the 8th meters per second, and my time, t is 10 microseconds, which is 10e to the minus 6 seconds, 10e to the minus 6. I'm going to get 30 when I multiply the mantisses, and I'm going to get E2 when I go 8 minus 6. 3,000 or 3,000 meters. Okay. Express the propagation speed in meters per microsecond. This is one I like to do. C is our velocity here, and it's 3 times 10 to the 8th meters per second. And this can be converted to microseconds by saying that 1 second is 1e to the 6th microseconds. And so I'm going to divide by 1 times 10 to the 6th. 8 minus 6 is 2, and I get 3e to the 2 meters per microsecond, or 300 meters per microsecond. The reason this is sometimes used in networking theory is that we really can imagine 300 meters. And, you know, a microsecond is 1/millionth of a second. And, you know, a millionth of a second corresponds to the bit period of a 1 megabit per second data stream. And so we're kind of used to thinking in terms of microseconds, which is a bit period of a 1 megabit per second. And we're kind of used to thinking in terms of, you know, meters, 100 meters, like a football field, 3 football fields in 1 microsecond. So that's sometimes used to help visualize the speed of light. Okay. Finally, this is the frequency used for many Wi-Fi systems. Suppose the bit rate for Wi-Fi signals is 11 megabits per second. How many periods of this wave are used for 1 bit? So this is kind of a different question. I'm going to make a time axis here, and I'm going to send some data, and I'm going to send data such that this little chunk of time is the bit period. Okay, this is the time to send 1 bit. So if we had, you know, it's like zeros and ones, we might have a signal that looked like this. 1, 0, 1, 1, 0. We might have a voltage signal that kind of looks like that in time. The voltage is a function of time. We might have zeros and ones kind of like that. So that's the bit period. And now we're asking ourselves, in time, we've also got this sine wave. This is we're sending a sine wave for a Wi-Fi system. And the question is, how many periods of the sine wave correspond to 1 bit in our data? And I will tell you to start off with, there are a lot more periods of the sine wave than there are bits. There are many periods of the sine wave for 1 bit. And we want to kind of know how many of these periods there are there, n, in 1 bit. And so what I'm going to do is I'm going to say, well, you know, whatever it is, the period of the sine wave is called t. Let's call that t. T is equal to the period of the 5.7 gigahertz radio wave. Okay? And I think we calculated that above, didn't we? No, we never did. We worked with the frequency, and we worked with lambda and the propagation speed, and we saw how far it went. We played around with the units, but we never did calculate the period, okay? So what I'm going to do, though, is I'm going to say that some number capital N times t is equal to the bit period. And the bit period is equal to 1 over the bit rate for the digital signal, in the same way that the period of the analog radio wave is equal to 1 over the frequency of that wave. And so what I can do is I can just rewrite this equation, and I have the n times t, but t is 1 over f, and the bit period is 1 over the bit rate. So I've just substituted in 1 over f for the t, which leaves the n in the numerator and the f in the denominator. And I've just flipped, and instead of tb, I put 1 over rb. And I'm trying to find that number n. It's some number of periods within 1 bit period. Okay? And so I can solve for n. N is equal to f over rb, the frequency of that 5.7 gigahertz radio wave divided by the bit rate. Okay? And I think I'm going to move this stuff down here. There we go. Maybe down to here. Okay? And maybe I'll just move this one over to here. Okay, so I've solved for n, and now I'm going to plug in the numbers that I have. I have the bit rate, 11 megabits per second. RB is 11 megabits per second, which is 11e to the 6th bits per second. So I'm going to write 11e to the 6th bits per second. And I'm going to keep the units on these numbers. And the frequency is 5.7e to the 9th hertz. Okay? And so the 9 minus 6 is a 3, right? So I get 1,000. And so 5.7 over 11 is 0.518. And this is cycles per second divided by bits per second. The seconds cancel, and I get cycles per bit. 0.518, and I forgot the times 10 to the third, rats. Okay. E to the 3 comes from e to the 9 divided by e to the 6. E3, which is 518. And the seconds cancel, and I get cycles per bit. And that unit makes sense. That's really nice because I was asking exactly how many cycles here, up and down, per 1 bit here. Okay, so 518 cycles per bit, and I think that's what I got the other day. I wrote 520, okay? In any case, that's how you do that problem. Hope that's clear. And finally, the last problem. Now, so we've done 3 different kinds of traveling waves. One was sort of this electrical signal on a wire, might be a USB signal, or something in your video wire. We did an infrared light problem. We did a Wi-Fi problem. And now we're going to do a sound wave traveling in air. Okay? This is 4 different physical situations that correspond to the same set of equations. The equations that we're using in all of these, and these are the ones to write on your little cheat sheet, are that frequency is 1 over the period. The propagation speed v is lambda times the frequency, the wavelength times the frequency. These are for analog signals. And I haven't had And that's basically all we've used, I think. Just f is 1 over t and v equals lambda f, right? Yeah, that's all I've used on this page. T is 1 over f equals lambda v. Yeah, I mean, I use, okay, yeah. And then here I did distances, velocity times time. For digital signals, we have corresponding equations. The bit rate, a frequency is a rate, and 1 over the bit period. And we also have that the number of bits being sent is equal to the time times the bit rate. The corresponding equation for that, let me move this one down here a little bit. Okay. The corresponding equation for our analog signal is that the distance is equal to the velocity times the time. Okay, so the distance that a traveling wave goes, and this is the number of bits. Okay. Again, we have a rate times a time. I could write this as RB times T. Okay. So those are the equations that we've used. Okay. We have not done this equation yet, but there is a corresponding equation here for the length of a bit. The length of a bit times the bit rate is equal to the distance hold on, let me think about it for a second here. Bits per second, meters per bit, meters per second. Yeah, this is the propagation speed. Okay, this is meters per second. This is meters per bit. This is bits per second. Okay? And so the length of a bit is literally the length of the voltage pulse on the wire. Okay, so this one we haven't done yet, but we will do that. I'll introduce the length of a bit in subsequent homeworks. In any case, these are the equations that we've been using. Okay. Frequency is 1 over t. T is 1 millisecond, which is 1 e to the minus 3 seconds. This is 1 over 1 e minus 3, which is 1 e to the plus 3 hertz. That's the frequency, 1 kilohertz. That's very typical of sound waves, okay? Calculate the wavelength. Okay, we have the speed. Velocity is 330 meters per second. That's already in standard units. So I can write that the velocity is the wavelength times the frequency, right? Meters, inverse seconds, meters per second. Good, that works out. I like to put little square brackets on my units. So lambda is, lambda is what I'm looking for, right? Yeah. Okay, so I have to solve for lambda. Lambda is V over F. Okay, I have both V and F here. I've got V is 330, and F is 1 e to the 3. And so this is 330 divided by 1,000, or 0.330 meters, or 33 centimeters. Does that agree with what I did the other day? Hey, I don't even have this one on the posted solution. Okay. Did I not do it? Okay, well, I'm going further than I did the other day. Express the wavelength in centimeters. I just did it here. Okay, so centimeters answer, meters answer. Express the low wavelength in millimeters. Okay, so 33 centimeters is 330 millimeters, I believe. Yeah, a millimeter is 1,000th of a meter, and here is a meter written with 3 decimal places. So 330 millimeters. 33 centimeters times 1 centimeter is 10 millimeters. 330. Right. Okay. And I think that does it. So I guess I went further than I did in the examples yesterday. And I also gave you a summary of some equations here. Well, I hope this helps. We've applied our traveling wave equations to 4 different physical situations. Electrical pulses on a wire, Wi-Fi, infrared light, either in the air or in optical fiber, and in a sound wave.